In this hour, we will use Laplace transform to obtain the response of an LTI circuit. The example that we will consider is the following second order circuit. Okay. Capacitor, here we have the input in our circuit, a resistor and an inductor. Okay, we have two dynamic components, and this is a second order circuit. Vs 1 ohm, 4/3 henries, 1/4 farads. This is the direction of inductor current, and this is our capacitor voltage, Vc. Now, for the input, the voltage of the source given as 4/3 e to the minus 2t ut volts. Find the zero state response for the inductor current, ILT. Okay, so that means since we're dealing with zero state response, we're going to assume all the initial conditions are zero, no initial charge on the capacitor and no initial flux on the inductor. Okay, and from the input we apply this waveform, and we'll try to figure out what type of what function for ILT this waveform generates in this circuit. Now, how we're going to apply Laplace transform to the solution of the circuit is this. We will first formulate this circuit, okay, and obtain the differential equation in time domain. And once we have that formulation, we're going to apply Laplace transform to that differential equation or integral differential equation and obtain the solution. Okay. Later on in this course, we will take that procedure one step further and apply Laplace transformation directly to the circuit and obtain an object that's called the S-domain circuit, and we will perform our analysis directly on that object without ever obtaining the differential equation for the circuit. Okay, but for now, let's obtain the time domain formulation first. We have three methods: node analysis, mesh analysis, and state equation. So let's apply each of them and make sure that each time we get the same answer. So let's begin by node analysis. Okay. It seems a particularly good choice because we have just a single unknown node voltage. So let's label it as E. Okay, and that means we're just going to have a single equation. So let's write that down by KCL. Okay, on that node, what we have is this current plus that current plus the inductor current equals 0. What's this current? It's minus the capacitor current, and capacitor current is capacitor current is capacitance times dVc, and Vc is Vs minus E. Therefore, minus the capacitor current is 1/4, and then we take the derivative of this difference, okay, E minus Vs. So that's the current through capacitor in that direction. And then we have the current through the resistor, which is E over the resistance, which is 1. And finally, we have the inductor current, IL. Now, since our formulation variable is E, we cannot write here IL. We have to write it in terms of the node voltage, which is the initial inductor current plus 1 over the inductance, and then we integrate the inductor voltage, and inductor voltage is same as the node voltage E. So what we have here is the inverse. Remember that this was our integral operator. Okay, and so this here is IL, and this sum by KCL must equal 0. Okay, so let's reorganize this equation. That is collecting the E terms on one side and throwing all the other terms to the other side. What we have here is 1 over 4 dE plus E and plus 3 over 4 integral of E. Okay, so that's our left hand side, and the right hand side is 1 over 4 ds dot time derivative of the input minus the initial inductor current. So let's call this equation 1. Before transforming this equation to Laplace domain, let's figure out the natural frequencies of our circuit. For that, what we need the node admittance matrix. In this example, in this case, since we have a single formulation variable, that matrix will be a one-by-one matrix. In other words, it's going to be a scalar. So let's write this as 1 over 4 d plus 1 plus 3 over 4 d inverse times E equals 1 over 4 dVs minus IL 0 minus. And this matrix, or scalar in this case, is our node admittance matrix. Okay, in this case, it's just a scalar y of d. What's the notation? Okay, so once we have the node admittance matrix, how we compute the natural frequencies was you replace d with s. S is our complex domain variable, and then you write y of s as numerator polynomial over denominator polynomial, and the roots of the numerator polynomial are the natural frequencies of the circuit. So let's do that quickly and figure out the natural frequencies for this second order circuit. Okay, now y of s equals 1 over 4s plus 1 plus 3 over 4s, and this written as a single fraction equals s squared plus 4s plus 3 divided by 4s. Okay, in other words, y of s equals s plus 1 times s plus 3 over 4s. Now, determinant of y of s being equal 0, well, in this case, y of s is just a scalar, therefore determinant equals itself. So what makes y of s equal 0? Either s equals minus 1 or s equals minus 3. And those two numbers are natural frequencies of our circuit. S equals minus 1 or s equals minus 3. Therefore, the natural frequencies of the circuit, or the modes of the circuit, are at minus 1 and at minus 3. Okay. Now, this was just a digression. We can now return to our actual problem, which is obtaining the zero state response for the inductor current. For that, what we're going to do is, let's transform our formulation in time domain to Laplace domain. So this is our equation 1. Okay, so let's transform that equation 1 to Laplace domain. Okay, Laplace transformation of equation 1 yields the following. Here we have 1 over 4 times E dot. So whenever we have a time derivative of a function, the Laplace transform of that function is s times the Laplace transform of the function who is being differentiated minus the initial condition. Okay. In other words, this term yields in Laplace domain S E. Capital E is Laplace transform of our lowercase e, okay, which is the time domain node voltage, minus E at initial time, 0 minus. Okay, so that's the Laplace transform of this term. And then we have Laplace transform of E, which is simply capital E. And then here we have an integral term, and Laplace transform of integral term is capital E divided by S. So this yields 3 over 4 then times E over S. And that equals the Laplace transform of this, which is 1 over 4 S Vs. Now that this is capital V, okay? This bar here indicates that it's capitalized. Capital V is the Laplace transform of Vs of t minus lowercase e, okay, at 0 minus initial condition. And finally, we have this term. What's the Laplace transform of this term? Well, this is IL 0 minus, so we're talking about a fixed number, a constant, okay? So our f of t is IL 0 minus, which is fixed, okay, for all times. Therefore, f of s is, whenever we take the Laplace transform of a constant signal, what we do is we simply divide it by s. So therefore, okay, therefore this guy produces minus IL 0 minus over s. And this here is the Laplace transform of equation 1. Okay, so what's E0 minus? Let's take care of that first. Now, since E equals, remember the circuit, Vs minus Vc, E0 minus should be Vs0 minus minus Vc0 minus. Okay, therefore we can replace this E0 minus by Vs0 minus minus V0 minus. And if you do that and collect the E terms on one side, this is what the equation becomes. S over 4 plus 1 plus 3 over 4s multiplying the Laplace transform of E equals S over 4 Vs minus 1 over 4 the initial capacitor voltage Vc0 minus minus IL 0 minus over S. Now, since we asked for the zero state response for the inductor current, we can take Vc0 minus and IL0 minus 0 and simplify the equation. But let's stick to the general case now. Let's take these guys 0 at the very end. Okay. So this implies E equals, we multiply both sides with the inverse of this function of S, okay, and that after simplification yields S squared over S squared plus 4S plus 3 times Vs, our input, minus S over S squared plus 4S plus 3 times the initial capacitor voltage Vc0 minus, and we have minus 4 over S squared plus 4S plus 3 times the initial inductor current. So let's call this equation 2. So that's E, and if you were asked for E of t, what we could have done is we could simply take the inverse Laplace transform of this and obtain E of t. But we're not asked for E of t, we're asked for the inductor current. So let's therefore express inductor current in Laplace domain using this equation too. So what we have is IL of t equals IL 0 minus plus 1 over the inductance, okay, so that's 3 over 4, and then we integrate the inductor voltage, which is the node voltage E. So that means in Laplace domain, the Laplace transform of the inductor current IL equals IL 0 minus over S, because it's constant, and the Laplace transform of a constant is that constant divided by S, and this produces 3 over 4S due to that integration times capital E. Okay, now this is IL, and we know what E is here in equation 2. So if we replace this E with this expression, we can obtain IL in terms of 3 things that it depends on, namely the input and also the initial values, initial conditions of the dynamic components. So this is equation, let's call it 3, and combining equation 2 and 3 yields the following. Two and 3 gives us the following expression for the Laplace transform of inductor current. IL equals 3 over 4 S over S squared plus 4S plus 3 Vs minus 3 over 4 1 over S squared plus 4S plus 3 Vc 0 minus, and finally plus S plus 4S squared plus 4S plus 3 times IL 0 minus. Okay, so as expected, IL depends on the input and also the initial conditions. Now, when you take the inverse Laplace transform of this equation, this part will give you the zero state response, okay, and this part will give you the zero input response, okay. So we can call this as the Laplace transform of zero state response, and here this is the part that depends on the initial condition, therefore it's called the zero input response. Okay. So for any initial conditions and for any input, we can now use this expression to compute ILT, the response. Okay, all we have to do is for the given initial conditions, we plug in Vc0 minus and IL0 minus, and for a given Vs of t, we obtain its Laplace transform and plug it in here, and then what we obtain is, we obtain for IL a rational function, a polynomial divided by another polynomial, and then by partial fraction expansion, we decompose that to first order terms, and then by inverse Laplace transform, we obtain IL of t. Okay, so let's do that for zero initial conditions, because we are asked for the zero state response for the inductor current. So zero state response of ILT for the input 4 over 3 e to the minus 2t ut is what? First of all, this is the time domain representation of the input. Let's transform it into Laplace domain, and it's very easy. It's simply 4 over 3 times 1 over s plus 2. Okay. Therefore, the Laplace transform of the zero state response of IL simply is this guy here times 4 over 3 times 1 over s plus 2. Okay, IL equals 3 over 4 times s over s squared plus 4s plus 3 times the Laplace transform of v of s, which we have just shown to equal 4 over 3 times 1 over s plus 2. And this can be simplified into s over a polynomial of degree 3. Here we have s plus 2 term, and this can be factored as s plus 1 times s plus 3. So we see directly where all the 3 poles reside. So this equals s plus 1 times s plus 2 times s plus 3. And we know that this can be written as the 3 first order terms, k1 over s plus 1 plus k2 over s plus 2 plus k3 over s plus 3. Now let's find the residues k1, k2, k3. And then we will be almost done. Okay, so what's K1? K1 is, so this is IL of S, and this is its factorized form. Multiply both sides with S plus 1. If you do that, that S plus 1 will cancel with this, and you're left with S over S plus 2 times S plus 3. And then you evaluate that expression at S equals minus 1, and that gives you directly K1. Hence, K1 equals S plus 1 times IL evaluated at S equals minus 1. So S plus 1 times IL, once again, is S over S plus 2 times S plus 3. Evaluate this at S equals minus 1, and that gives us minus 0.5. Okay. K2 likewise equals S plus 2 times IL evaluated at S equals minus 2. So what we have is S over S plus 1, S plus 3 evaluated at S equals minus 2. And that is 2. Finally, K3 reads S over S plus 1, S plus 2, put S equals minus 3, and that should yield minus 1.5. Okay, now we know K1, K2, K3. What remains is just transform these very simple first order terms to time domain, which reads as follows: IL of t equals K1 times e to the minus t plus K2 times e to the minus 2t plus K3 times e to the minus 3t. So 2e to the minus 2t, let's write this term first. And then let's write remaining terms. 1 over 2 e to the minus t minus 3 over 2 e to the minus 3t amps for t positive. Okay. Now, let's look at each term separately. Here we have e to the minus 2t term, and this is our input Vs of t, which contains e to the minus 2t. Therefore, this e to the minus 2t term must be coming from the input, and that term therefore is no other than the particular solution. Okay, so this is our particular solution piece of the zero state response. And the remaining terms, we have e to the minus t and e to the minus 3t. Remember that natural frequencies of the circuit were at -1 and -3. Therefore, this piece here is the homogeneous solution part of the zero state response. Okay, so this is the homogeneous solution. Okay, so the problem is solved using Laplace transformation. Now let's resolve the problem, this time using a different formulation, okay, namely mesh formulation. So now let's apply mesh analysis to the same circuit. Again, what we're after is we're after the zero state response for the inductor current for the given input waveform. Let me redraw the circuit. VC, this is IL, and here we have VS. Okay, so we have two meshes. Let's call the mesh currents as I1 and I2. Okay, since we have two formulation variables, so that means you will have two equations, and put in matrix form, that will produce a 2x2 mesh impedance matrix. So KVL at first mesh, mesh 1 reads, so we're traveling in clockwise direction. Starting from this point, we have minus Vs, okay, plus Vc, which is Vc0 minus plus 1 over the capacitance. Then you integrate the capacitor current, and capacitor current is no other than the first mesh current, the inverse I1. And finally, plus the voltage of the 1 ohm resistor, which is 1 times I1 minus I2. And by KVL, this produces 0. Let's do the same thing on the other mesh. Okay, starting from this point, we have this voltage plus minus, which is 1 times I2 minus I1. And then we have the inductor voltage, which is 4 over 3 DIL, and IL equals to I2. So we have 4 over 3 DI2, and that equals 0. So let's call this set of equations star. Eventually we will transform these equations into Laplace domain in order to obtain the solution. But before that, let's obtain the matrix form of those equations and see clearly the mesh impedance matrix. Okay, so rewriting set of equations star here produces the following matrix equation equals S. So here we have the vector that contains our formulation variables, namely the mesh currents. Okay, for the first row, let's look at the first equation here. For I1, we have this integral term and this term with coefficient 1. So therefore we have 4d inverse plus 1 for I1. For I2, we have only this term, minus 1. And all the other terms we throw to the other side. We have Vs over there and minus Vc0 minus. For the second row, let's look at the second equation. For I1, we have this term, minus 1. For I2, we have 1 here and 4 over 3 d. 1 plus 4 over 3 d. And that's all. That means we have nothing on the right-hand side. And this matrix that appeared here is our mesh impedance matrix, Z of d. Now, let's take this set of equations and transform them into Laplace domain. Laplace transformation of equations star produces, okay, for the first equation we have minus capital Vs, okay, so this is the Laplace transform of Vs here, and here we have a constant signal Vc0 minus. The Laplace transform of a constant signal is that constant divided by S plus Vc0 minus over S. Then we have this integration. So in Laplace domain it's 4 times Laplace transform of I1 divided by S. 4 over S times I1. And then the remaining terms are easy. I1 minus I2. And that equals the Laplace transform of 0, which is 0. Okay, and the second equation yields I2 minus I1. And here we have 4 over 3S I2 minus lowercase I2 0 minus, okay, minus I2 0 minus. And what's I2 0 minus? I2 is IL, therefore I2 0 minus is IL 0 minus. And that equals 0. Okay. And since we are interested in the zero state response, so let's simplify this equation a little bit by setting Vc0 minus and IL0 minus to 0. Okay. This yields, by letting the initial conditions equal to 0, the following. Okay, something times I1, I2 equals the right hand side. Okay, here we have, okay, now this term and this term, they went away, and here we have 4 over S plus 1 minus 1, and this is Vs. And here we have minus 1, 1 plus 4 over 3S. Over 3S, and here we have 0. Okay, now that this matrix is no other than Z of S, Z being our mesh impedance matrix. This is our Z of S. Now, since we have our Z of S, let's use it to compute the natural frequencies and see whether they equal the natural frequencies that we obtained using node formulation, which were at -1 and -3. Since natural frequencies are independent of the formulation choice, they are inherent properties of the circuit itself, and the circuit doesn't care which way you use to formulate it. It must be the same at -1 and -3 when you use mesh impedance matrix to compute them. So let's do that. Let's compute the determinant of Z of S, which is this guy times this minus 1. 4 over S plus 1, 1 plus 4 over 3S minus the square of -1, which is 1. And that, after simplification, reads 4S squared plus 16S plus 12 over 3S, and that can be written as 4S plus 1, S plus 3 over 3S. Okay, clearly S equals -1 and S equals -3 are what makes this determinant 0. So the natural frequencies must be at -3 and -3, -1 and -3 as expected. Okay. Now, finally, let's obtain the zero state response for the inductor current. Since inductor current is I2, so we're after I2. So what's our formulation variable vector? I1, I2 in Laplace domain equals the inverse of mesh impedance matrix times this vector, Vs0. Okay, the inverse of mesh impedance matrix is 1 over the determinant, and the determinant is here. So that reads 3S over 4S plus 1 times S plus 3. And then we have the adjugate. We swap the diagonal terms. Okay, and we negate the anti-diagonal terms, 1, 1. And then we're multiplying that by the vector on the right-hand side, Vs0. Okay, this is IL, this is what we're interested in, and I2 equals what? 1 over the determinant times the second row times this vector. And that yields IL equals I2, and that equals this times that is simply 1 times Vs, because this is 0. So we're talking about this times Vs, 3S over 4S plus 1 times S plus 3 times the Laplace transform of Vs. And from this point on, we already did the same thing for the node analysis method, so we know the answer. This is the zero state response for the inductor current. Same as before, as expected. Okay, for the last part of our question, let's redo the whole thing, this time using the state equation, and we will have the complete package of formulation choices. Okay, the last part, we reformulate the circuit by state equation. Okay, this is our circuit. Vs, Vc, 1 ohm, inductor current IL. Okay. So we have, okay, the state variables are capacitor voltage and inductor current. So to obtain, therefore, x dot equals ax plus bw, in this case bvs, we have to figure out what's vc dot and what's il dot. For vc we have, okay, 1/4 dvc, which is the capacitor current. Capacitor current equals this current through the resistor plus IL. And what's this current? This current is Vs minus Vc over 1. Okay, 1/4 dVc equals IR plus IL. And that's Vs minus Vc. This is Vr plus minus over 1 plus IL. Okay, so that's a nice equation because it's only in terms of the formulation variables, this time capacitor voltage and inductor current, and the input Vs. And as for the inductor, we have, again, starting from the terminal equation, LdIL equals what? VL. The inductor voltage. Inductor voltage is resistor voltage, and resistor voltage is here, Vs minus Vc. So that equals Vs minus Vc. Okay, so let's reorganize these equations. So what we have here is dVc, multiplying both sides with 4, yields minus 4 Vc plus 4 IL plus 4 Vs. And multiplying both sides with 4/3 yields dIL equals minus 4/3 Vc plus 4/3 Vs. Okay. So, since our state vector is composed of capacitor voltage and inductor current, all we have to decide is which is first and which is the second state variable. It doesn't really matter, so let's go with Vc, the first state variable, and IL, the second state variable. Okay, for this state choice, what we have is x dot equals ax plus b times the input. This is our A matrix, this is our B matrix. What's A matrix? We look at this equation here for the first row, because Vc is our first state variable. Vc dot equals minus 4 Vc plus 4 IL plus 4 Vs. Okay, what's IL dot? IL dot is 4/3 Vc plus 0 IL plus 4/3 Vs. And this is our state formulation. Now, once we have the formulation, once we have the differential equation, what we do next in this example is we apply Laplace transformation to it. So let's do that. Laplace transform. So here x dot yields s times the Laplace transform of this vector, okay? And the Laplace transform of a vector simply means the Laplace transforms of its individual entries, okay? So here x therefore is Laplace transform of x is Laplace transform of Vc and Laplace transform of IL, that vector. Okay, and here we have the initial condition term, because Laplace transform of x dot is Sx minus x0. So that's the left hand side. How about the right hand side? We have A is a constant matrix, therefore this simply is A times the Laplace transform of x and Likewise, B is a constant matrix, so what we have is B times the Laplace transform of the input, Vs. So let's collect the x terms on one side and throw everything else to the other side. If we do that, we have Si minus A, a 2 by 2 matrix in our case, times the Laplace transform vector equals x0 minus plus b times the input. Hence, Laplace transform of the state vector equals, multiply both sides with inverse of this matrix. We have Si minus A inverse times initial condition vector plus Si minus A inverse times B times Vs. Okay. Now this clearly is the zero input response because it's part of the response due to initial conditions. Eventually we will let that zero because we're considering this zero state response. So this is zero input response. Okay, and here is zero state response. Okay. Once we have the state formulation, we can also easily obtain the natural frequencies. Note that natural frequencies of a circuit is the eigenvalues of the A matrix that appears in state equation. So, since we have already obtained, using other formulations, that natural frequencies are at -3 and -1, it must be that the eigenvalues of this A matrix here must be -1 and -3. So let's quickly check that. All we have to do is figure out the so-called characteristic polynomial, which is the determinant of this matrix, Si minus A. S plus 4 minus 4 Okay, so I made a mistake. This here should be right, -3/4 and 3/4 here. Okay, and then this appears as 3/4, and here we have S. Okay, so the determinant then is S times S plus 4 plus 3, which is S squared plus 4S plus 3, which is S plus 1 times S plus 3. Hence, the roots of the characteristic polynomial are at -1 and -3, so that means the eigenvalues of A matrix are -1 and -3. Equivalently, the natural frequencies of the circuit, or the modes of the circuit, are -1 and -3. The natural frequencies are at -1 and -3. Okay, and finally, let's obtain the zero state response. For that, we have to compute this inverse. Okay, Si minus A inverse equals 1 over the determinant, and determinant is here, 1 over S plus 1, S plus 3, times swap the diagonal terms and negate the anti-diagonal terms. Okay, so that's our Si minus A inverse matrix. And then we have VCIL. This is the Laplace transform of our state vector. VCIL equals Si minus A inverse times B times Vs. and that equals 1 over S plus 1, S plus 3 times S4 minus 3 over 4 S plus 4 times B4 3 over 4 times Vs. Okay, since we're asked for IL, it equals this times second row times B times Vs. Okay, so IL equals 1 over S plus 1 times S plus 3 times the second row minus 3 over 4 S plus 4 times the B matrix 4 3 over 4 times the Laplace transform of the input, and that reads 3 over 4 times S plus 1 times S plus 3 times Vs, the input. This is the zero state solution for the inductor current, okay, which matches, as it should, with our previous answers that we obtained using different formulation methods.